Because of the fact that a more powerful theory has emerged out of this Sinanoglu's idea of pairs and their product of pairs being important, and that has subsumed the entire set of electron pair theory, and that is known as the coupled cluster theory. So, that is essentially much more powerful method, and that has subsumed the most of the discussion of the electron pair theory, and also subsumes all of perturbation theory. Though perturbation is independently exist, and most of the electron pair. This is a very debatable points, of course, because there are a lot of people in Europe, particularly in Germany, who actually work on electron pair approximation. As you can see from the name, Wilfried Meyer is from Germany, and many of the German scientists are very attached to electron pair theory. The coupled cluster was invented more in the United States, of course. Then later on, of course, it has gone to US, but it was originally done. Originally, there are two Czech scientists who actually did it in atomic and molecular physics. One of them, who is basically called a pioneer, is Jiří Čížek. He was a Czech, but I think during the war, I mean those days, you know that there was a lot of tough time in Eastern Europe. He actually fled from Czech Prague to Canada, and eventually got a job in Canada, and then he actually was doing the coupled cluster along with Joseph Paldus. So, both of them actually did a lot of initial work in on coupled cluster, and they were based in the North America, I mean in a broad sense Canada, and of course eventually it went to Rod Bartlett in the US, in the Florida, and of course Europe became very active, because you know they understood that it is in a way much more sophisticated version of the pair theories. But I must say that the pair theories themselves were extremely important part of the coupled cluster, you know, origin. It started also from Sinanoglu actually. So, I must say that Sinanoglu gave the original idea, then Wilfried Meyer developed. So, the Germans are still very sometimes get very upset, the old German scientists, that the United States stole from Germany the coupled cluster actually in some way. So, this is basically a North American start. And as you know, when the United States takes over, they can advertise well. So, the coupled cluster became so well advertised that it almost finished off the electron pair approximation. So, there is a lot of discussion on that. But if you look at the philosophy of the coupled cluster, in a way Wilfried Meyer was already doing coupled cluster, but he again could not give the exact notations and how to do second quantization and so on. Coupled cluster uses a lot of second quantization, diagrammatics, which I already discussed for the perturbation, very similar. And eventually it was a very nice size extensive theory. So, it takes care of the dynamic correlation very well. So, normal standard coupled cluster is size extensive, which means it has correct n dependence. So, if you combine with the reference space, if the reference Hartree-Fock or whatever reference space fragments independently, dissociates independently, and this is a very important point which you know that was not followed in DCI, to the correct limit, dissociation limit, then the approximate couple cluster, any approximate couple cluster, also separates correctly. Note that these 2 points are little bit tricky. First, we are saying that the standard couple cluster is always size extensive, which means for a given n electron problem, the energy, correlation energy goes as proportional to n. However, for dissociation or separation, I need to ensure that the reference space must fragment independently. If reference space does not fragment independently, even if you do couple cluster, standard couple cluster based on this reference, and I will tell you how it is done, this will not achieve size consistency or size, this is called size consistency, right? We have already mentioned this is size consistency is basically dissociation. So, please remember there is a slight difference between size consistency and extensivity. Extensivity is merely correlation energy being proportional to n. Size extensivity consistency is giving the correct dissociation. But for that, one important part is the reference function must dissociate correctly. So, if I start with the RHF, and I again want to repeat, for Li2, Li plus Li, right, it does not dissociate correctly. So, whatever you do after this, it will not help. So, even if I do couple cluster on this RHF, although couple cluster is size extensive, dissociation won't be achieved, right. On the other hand, you look at Ci, for the Ci what happened, the RHF was correct, H4 going to H2 plus H2 was alright. Then I did a DCI, then this separation could not be done. This will never happen in couple cluster, because the reference space, if the reference space correctly separates, couple cluster will guarantee the dissociation, it will not spoil. So, it is very important to realize that the reference space dissociation is not necessarily retained by approximate theories. When I do any approximate theory, perturbation does. I actually mentioned that perturbation also is size consistent, just like couple cluster. I mentioned that yesterday, that they have the right n dependence, and hence it is size consistent. So, for size consistency, theory must be size extensive. There are two important points. Reference space must fragment correctly. And I had written down once that these are the two features for size consistency, that this has to be there and this first part has to be there. If both are there, it will guarantee dissociation, which the couple cluster does, which the perturbation does. But Ci does not, because Ci, the approximate Ci does not, because it violates this first part. Of course, approximate, full Ci will do anyway. There is no discussion on full Ci. Full Ci is exact function. Okay. So, I think that is essentially something that you have to remember about the feature of the couple cluster. The couple cluster can take care of this DCI problem of H4, H2 plus H2. If you remember why the DCI problem was very difficult, because when I did H4 DCI, it had a doubles, right, which was only 1 bar to 1A bar to 2A bar, and 1B bar to 2B bar, right, at the separation limit. But when I take the product function, the product must contain a quadruple, which was 1A bar. I just look at the dimer, for example, 1B bar, 2A bar, 2B bar, right. With the coefficients, this product has coefficient, it means coefficient as the product. I think we have discussed this, that not only you require the quadruply excited, but its coefficient cannot be a linear function. It has to be a product, and that time I mentioned that no linear answers can actually give it, but an exponential answers can. So, this is exactly what the couple cluster do. So, exactly what the couple cluster does is to start from a Hartree-Fock standard couple cluster. I will not go into the details, the more details than that. The standard couple cluster, which is basically a single reference based. So, you will understand the meaning, single reference couple cluster, or CC. So, it starts from a psi Hartree-Fock, and instead of writing 1 plus linear expansion, it gives a expansion in terms of exponential of a creation operator. These T now are just like Ci, it generates one particle excitation, two particle excitation, three particle excitation. So, in terms of holes and particles, it is whole particle creation operator, right. If I consider the Hartree Fock as a vacuum, I have already mentioned that everything that you do is a whole particle creation. Either you create whole and create particles, and you have, just like in Ci, you have CISD, so you can have a CCSD depending on what is the T. So, T in general is T1 plus T2, etc. up to Tn. So, just like Ci, this is actually one body excited, two body excited, up to n body excited. So, you can actually generate several excited determinants by action of this T operator on Hartree Fock, just the T operator. But since the coupled cluster wave function, the phi coupled cluster is actually exponential T and not 1 plus T, it guarantees this product. Okay, and this is something I mentioned before. I will not go into the details, because the exponential of this into exponential of this is exponential of two sum, T sum A and B. So, it guarantees the exponential separation, guarantees the product, and this is why it does. But otherwise, the T1, T2 looks like exactly Ci operators. So, can we write what is T1 for example? It is a one body excitation operator. So, in normal quantization, what we will write like this: A P, some amplitude, let me call it TAP, and A P dagger A, correct, in operator form. So, what is it doing? When it acts on Hartree Fock, it annihilates an electron from occupied orbital A and creates an electron in unoccupied orbital P. So, it generates a determinant psi A subscript P superscript, correct, with a coefficient which is TAP. The coefficient is also important. So, when I take exponential of T1, then you have the coefficient product, T1 square, T1 cube, and those things will guarantee that product separation that I talked of. Similarly, I can write T2 as sum over A less than B. This is all doubles, P less than Q. I write T A B P Q, just like I used to write in Ci C A B P Q, remember? So, I am writing T A B P Q, A P dagger, A Q dagger, A B A A. Again, note the order, because I want B to be replaced by Q. So, the order has to be changed in second quantization, just like I wrote the 2 electron operator and I have T A B P Q, and I made it A less than B, P less than Q. If you make these A, all B, all P, all Q, you have to put a factor 1 by 4. These are all spin orbitals. So, similarly, I can generate T3, T4, etc. Each of these acting on psi Hartree Fock will actually generate determinant, but it is not Ci, because the final wave function is not 1 plus T1 plus T2 plus Tn. That is the difference from Ci. It has an exponential T. So, the product will come, and hence lots of nice things that which have to be taken care are taken care by coupled cluster. Of course, the calculation of these T amplitudes is much more complex. I will not get into it. In Ci, since it is a linear expansion, one can show that this becomes a simple eigenvalue problem. Here it is not. In fact, the equations become much more complex, and they have a structure of a nonlinear equation, algebraic nonlinear equation. You can imagine why they would be nonlinear, because you have this exponential T, and that makes it rather difficult. It's not difficult, but it is more time consuming than Ci, I should say. And today people know how to solve nonlinear equations by iteratively. Again, iterative techniques are usually used, and you can actually show a lot of correspondence with perturbation theory. So, some correspondences can be shown. When you do the iteration, just like we showed, you need to Ci iteration. Remember, under some approximation we got PT2, perturbation theory 2. Here it is much more easy to show the orders of perturbation, MP2, MP3, etc., etc. It's much more easy to show, and I will not get into this, but I just thought as an overview I will mention that the equations become more complicated, which you should imagine. I mean, you can't have everything good, right? I mean, so you have to compromise on something. So, the standard coupled cluster, of course, you have a problem here if this reference space does not fragment, I told you. in that case you can actually have a reference space which is like MCSCF or multi-configuration, then the exponential T. So you can do both good static and good dynamic correlation. They become part of what are called the multi-reference on CC, MRCC. Again, those are extremely advanced and probably the state-of-art correlation theories today. In that when I take this as a reference space and then I put exponential T, so they become the reference things today. I should just mention for 1 minute that all the discussion that we have done is based on calculation of wave function. Right from the beginning, if you remember, was to solve H psi equal to T psi. So if you ask me, what did we do in all these 38 classes? And I have to say we tried to solve H psi equal to T psi, right? And that equation that we are solving, lest you forget, it's just H psi equal to T psi. Started many particle. Okay, single particle, of course, we are great expert. Particle in a box, harmonic oscillator, that we did. We went to many particle, and then we said because of this 1 by R12 term, it is not exactly solvable. Then we got into all this mess. So we said, let's make a simplification, let's make a model non-interactive problem, a single determinant. That gave rise to Hartree-Fock because we already knew a lot about variation method, how to do this. And then we said not good enough because you are missing that 3%, 3 or 4% of the total energy, which is very, very important for chemistry. Then we went to electron correlation theory. We did CI, further mess because what was good became bad in double CI, but results are better, of course, lower than the Hartree-Fock. Then we went to perturbation theory, how to handle complicated perturbation. We taught diagrammatics, and then we found that something more to do because higher order perturbations are very, very expensive. Coupled cluster can do better. So we went to coupled cluster later, and then of course in between we talked of MCSCF today. So all this is really to solve H psi equal to T psi, to get a structure of psi, many particle psi. There is another theory which does not talk of wave function at all, which directly talks only of density. And I said the density is of course related to the wave function by very simple formulae, which I will just give you, that given the wave function, and this is important to know, R x2, sorry, x, x2, x3, xn, psi, x, these are all vectors, 4-dimensional quantities, x2, xn, integrate over dx2 to dxn completely, and for the x part integrate only the spin. So if you see, it's a very complicated n-1 particle integration that I am performing. One of them is left untouched, x1 or whatever dummy variable you can call it. For that you integrate the alpha and spin part, then I get a quantity multiplied by n. I got a quantity which depends only on a 3-dimensional variable, R. So what we are suggesting is that this is actually density. If you do a simple Hartree-Fock, where psi is simple Hartree-Fock, this density was sum of the orbital densities. Actually it can show this, but this is for a general definition of density. So there is a different class of theory which does not even talk of psi, which basically builds the energy directly as a functional of density. Potentially, this is simpler because the density is just a 3-dimensional variable. Remember, even if this is an n-electron problem, the density is just a 3-dimensional variable. So it is very nice if I can write energy as a functional of density and not functional of psi. This was possible due to a very important theorems by Weinberg and Kohn, who actually showed that this existence of energy, ground state energy, I must say ground state energy only, as a functional of electron density is possible, but nobody knows how to get this exact function. So there have been lot of efforts to get exact functionals, and particular difficulty has been to get the kinetic energy, exchange, as well as correlation. So all important things, and lots of approximations have been done. All these, then you can, if I have a functional, I can get this energy to be optimum with respect to density, just like variation method, and I get what is called today DFT. but it's like wave function. There are so many things because you can keep on changing this functional. There is no functional which people know which is correct. The biggest problem with DFT is, of course, the advantage is simplicity, but the problem is that there is no systematic way of improving this function. We don't know what is better, and so on. So that's a real problem. I didn't discuss DFT in this course, neither it was part of the scope of this course, but I just thought I'll mention about DFT, that this has come out as a very, very popular method. And today, if I say I'm teaching to a layman, if I say I'm teaching advanced quantum chemistry, they would assume that I have taught DFT. And somebody told me, oh, you have taught so many classes of DFT. I said, no, I did not teach DFT at all. So it's an embarrassment to actually clarify that I'm not teaching DFT, and it is a part of quantum chemistry. So, but DFT has become such important thing for experimentalists. So at least you should know that, I have not taught DFT. So first, but DFT is important. So I thought I'll mention this. The DFT connects to the wave function through this. The density connects to the wave function through this formulae. Okay, so I think with this I will close